Welcome all to lecture 7 of CS 302 data structures. I'm Dr. Sangeeta Bhattacharya, and in this lecture we are going to see the following two things about the application of array and linked list in representation of sparse matrix and a polynomial equation. Let us first start with the sparse matrix. So a matrix is defined as a matrix is a two-dimensional array with m number of rows and n number of columns. So this is a typical definition. We can think of it in terms of implementation in computer. So it can be thought of as a two-dimensional array with m number of rows and n number of columns. So we can think of a matrix like this: 2, 4, 8, 10, 5, 20. And when we represent a matrix like this, so it is having m number of rows, that is 2 number of rows, and n number of columns, that means 3 number of columns. And in that case, it can be represented by 2 cross 3. That means the representation can be done by m cross n. So any matrix can be represented by m cross n dimension. So this is the dimension of this array. Now, if we have to implement this matrix using an array in any programming language in computer, the total number of spaces which will be required is very easy to calculate. So the memory space required for storing a m cross n matrix will be equals to m, that is the number of rows, that is m, into number of columns, n, into size of the data type stored. So typically if it is int, it will be 4. If it is float, it is 4. So this is the memory space which will be required for storing a m cross n matrix in memory. Now, if our matrix is like this, so our matrix, this is my new matrix, which is having 5 number of rows, 6 number of columns, and the elements are something like this. So you can see this matrix that it is containing more number of 0 elements than non-zero elements. So the number of non-zero elements in this matrix is very less than the number of 0 elements in this matrix. So this is my matrix. So how many total number of memory spaces which will be reserved for this matrix? So let us go back to the previous formula which we have written. So the memory space reserved for this storing this particular matrix will be equals to the, so this matrix is of dimension 5 cross 6. So this is a 5 cross 6 dimension matrix. And the memory space reserved in this case will be equals to the number of rows, which is 5, into the number of columns, which is 6. And because this is an integer matrix, so the memory space reserved will be 4. So it will be equals to 120 bytes. So 120 bytes of memory space will be reserved for this, storing this matrix, out of which most of the elements are 0 elements. This type of matrices, where most of the elements are 0 elements, are known as sparse matrix. So sparse matrix is a matrix. So this is known as a sparse matrix. So a matrix which contains more 0 elements than non-zero elements. This is the definition of sparse matrix, which store more number of 0 elements than non-zero elements. Now, in this particular example, if we see, to access the 6 non-zero, so out of 30 elements in this particular matrix, only 6 are non-zero elements, and to access the 6 non-zero elements, the number of access will be equal to the dimension of the matrix, which is 5 cross 6 equals to 30. So we can see that if we want to represent a sparse matrix using the normal array representation, it leads to wastage of memory space. Because this matrix is very small dimension, 5 cross 6, it is leading to only 24 memory spaces are getting wasted because of this. But if we think of a matrix of dimension, suppose 10 cross 100 cross 100 matrix, in which number of non-zero elements is only 10, we can imagine that how much 90% of the memory space is getting wastage because of storing only 10 number of non-zero elements. 90% of the memory space which we are going to use for this matrix is going to get wasted. So this is the reason why the sparse matrix representation is of utmost importance, because sparse matrix is used in different kind of applications like machine learning, which is a very growing field nowadays. And if people are programming like that, they require to know what is the efficient way of storing a matrix containing more number of 0 elements. Now you can see that here the time complexity is of not much importance, but rather the playing factor is the space complexity. So this is the term which is because of what we are talking about, the different representations. And here space complexity for representation of a sparse matrix using a normal 2-dimensional array is leading to wastage of memory space. Now, we will be coming to the representation of the sparse matrix. I will be taking a very small example, and with the help of that, I will be explaining to you. So let us consider. So first, we are going to see the array representation. So array representation of sparse matrix. And in the array representation of sparse matrix, let us take the example by which we are going to do. So I'm going to take a very small example. So let my array be something like this. So this is a very small example where it is of dimension only 3 cross 4. So it is a 3 cross 4 dimension. And here we are going to see how we can represent this particular matrix using both array and linked list. So this is our sparse matrix, and here we can see that it's a 3 cross 4 dimension matrix and the number of elements are 3. And if we want to represent it using a sparse matrix, then it will be first a 2-dimensional matrix array. So we can see here, you can see here it's a 2-dimensional array. So this is a 2-dimensional array. Next, the number of rows in this 2-dimensional array will be the number of non-zero elements plus 1. Because the number of non-zero elements in a sparse matrix are limited, so it will be the number of non-zero elements plus 1. Why 1? We will come to it after a certain point of time. The number of columns will be fixed, which is equals to 3. And why this 3? The 3 will be because of noting down the row number of the non-zero element, the column number of the non-zero element, and the value of the non-zero element. So this 3 is fixed for representation of any sparse matrix which will be given, and it will always be 3. Well, the number of rows will depend on the number of non-zero elements present in the sparse matrix. So it is going to be variable for each of the sparse matrix which we are going to represent. And in this representation, the first row will be the unique, because in the first row, we have to note down the following information about the total number of rows present in the sparse matrix, the total number of columns in the sparse matrix, and what is the total number of non-zero elements present in the sparse matrix. So the first row of this 2-dimensional array will be reserved for the following 3 informations. So let us do that for our given example. So I have already drawn this, and you can see that there is a row number, there is a column number, and there is a value field. So these 3 are the 3 columns which will be fixed for any sparse matrix. Now what will be the values? So in the first row, we will have to note down the number of rows, number of columns, and the number of non-zero elements in the sparse matrix. So we can see that our sparse matrix is of dimension 3 cross 4. So in the row column, it will be 4, column it will be 4, and the number of non-zero elements are 1, 2, and 3. So it is going to be 3. After the first row, we are going to show the information about the non-zero element. So what is the non-zero element? So again, the row. So let us first go and check the first row. Is there any non-zero elements? Yes, there is a non-zero element. Where is it? It is there in the second row. Now always remember, whenever we are representing it, we are going to start from the 0. So we have already seen the indices starts from 0. So this is 0, 0, 0, 1, 0, 2. So where is it? It is in the first row, second column, or it is in the 0th row, second column. So we will come back here. And what we are going to note down? We are going to note down 0, that is a 0th row, second column is having a non-zero element 1. Similarly, the first row, 0th column is having the non-zero element 2. The second row, first column is having the non-zero element 3. So, well, in this case, if we have to reserve the memory space for this, then the memory space required will be equals to 3 cross 4 because that is a dimension, and 4 because it is an integer matrix. So it is 12 into 4, 48 bytes. Well, if we see the memory space which will be used for this case, it will be memory space for representation of the sparse matrix using this notation. It will be equal to the number of rows. So it is the number of non-zero elements plus 1. So we can represent it like this. So number of non-zero elements plus 1 into 3. The number of columns is 3. So number of columns into size of the data type. So for our example, we can think of it as equal to, so in our example, it will be equal to the number of non-zero elements is 3 plus 1 into number of columns is 3 and the size is 4. So if we 4 cross 3 into 4. Now in this case we see that the bytes reserved for this example is not much, because here also we are reserving space for 12 elements. Here also we are reserving a space for 12 elements. But because we have taken this to be a very small example, in this case we cannot understand the significance of the array or representation. But if we are thinking of a large sparse matrix having many non-zero elements, then this example is going to be, this representation is going to be very effective. So this is known as the triplet representation of sparse matrix using array. Triplet representation of sparse matrix using array. Next, we will see the linked list representation of this, because even we have represented the sparse matrix using this array, you can see that if we are considering a very small example like this, in both the cases, it is taking up the same memory space. So next we are going to see the linked list representation of the sparse matrix. And let us check how we can do it efficiently. Now, for the same matrix, if we see the linked list representation, then it is like this. So there will be 4 fields. The first field will be for the storing the row number of the non-zero element. The second field will be for storing the column number of the non-zero element. The third field will be for storing the value of the non-zero element. And the fourth field will be the pointer to the next non-zero element. Typically, the address of the next non-zero element means the address of the element in the row which is having the first non-zero element after the noted non-zero element value. Now, we have already seen that if we want to implement a single linked list, there are in particular 2 fields. One is the value field and one is the next pointer field. But when we are representing in case of a sparse matrix, it will be having three values. The first one will be now all these three values we have kept it as integer because we typically the matrix contains integer values. So the first one will be for the row number of the non-zero element. The second one will be for the column number of the non-zero element. The third one will be for the value of the non-zero element. And the fourth one is the pointer. It's a self-referential pointer to the next, which will store the address of the next node or the next non-zero element in the sparse matrix. Now, how we will be representing it? So the representation is very simple. So first is the start node, which contains the address of the first non-zero element. In the first node, we are storing, so we can see in the sparse matrix, the first non-zero element is in the first row, second column, and the value is 1. So that is what has been noted here. So 0 for the row number, 2 for the column number, and 1 for the value. Then the next pointer contains the address of the next non-zero element in the sparse matrix, which is 2, and which is present in the first row, 0th column, so 1, 0, 2. Similarly, it contains a pointer to the next non-zero element, which is stored in the second row, first column. So this is how we can represent the sparse matrix using a linked list representation. And naturally, if we talk about a linked list representation, here the memory space which will be reserved is less compared to the array representation. So generally for sparse matrix representation instead of array, linked list representation is preferred. In the next topic, we will be seeing how application is the polynomial representation using both array and linked list. So let us start with the polynomial representation. So a polynomial representation, what is a polynomial? First let us know. So we all know a polynomial equation can be represented like this: an x to the power n plus an minus 1 x to the power n minus 1 dot dot dot, so that we go till a0 x0. So this can be represented as the summation of I equals to 0 to n ai x to the power I. Now what is this term ai known as? So this term is known as the coefficient of the polynomial, and n, this power n is known as, or this I is known as the exponent of the polynomial equation. So each polynomial equation consists of two parts. One is the coefficient part and other is the exponent part. So let us see an example. So we can have a polynomial equation like this: 10x cubed plus 2x square plus 1. And in this polynomial equation, you can see that it is not necessary that all the exponents starting from 0 to n should be present. Any of the exponent may not be present. That means that polynomial, that exponent coefficient is 0. So this we can represent like this. So 10x cubed plus 2x square plus 0x to the power 1 of 0x plus 1 into x to the power 0. So this polynomial in short form we have represented in this form. So this polynomial we have represented in this form, in the short form. So here 10, 2 and 1 are known as the coefficients. The exponents are 3, 2, 0. And this coefficients a0 to an, they should be real numbers. So they can be either integer values or floating point numbers. So they are basically real numbers. But this I, that is the exponent, should always be a non-negative integer. And n, that is the highest exponent in a given polynomial, that is n, is known as the degree of the polynomial. So this is known as degree of the polynomial. Now, if we have to represent this polynomial in computer memory, the three important points which we should note down is that the first point is that the coefficient of the coefficient and exponent sign should always be stored along with the coefficient and exponent itself. That means if we have a polynomial, suppose 2x squared minus x plus 10 here, this is actually can be written like this: 2x squared plus minus 1. So basically the coefficient of the term x is minus 1 plus 10. So this minus sign of the coefficient of x should be stored along with the coefficient. Similarly, in case of exponent also, we have to do the same thing. Though in case of polynomial, we have told it is a non-negative integer. So the sign of the exponent will never be negative. The sign of the coefficient only can be negative, because we have already told the exponent will always be a non-negative integer. The second important point is that each exponent should have only one term. That means we cannot have something like this: 2x squared plus 3x squared plus 5x. In this case, we can see that x squared has two terms, one with coefficient 2 and one with coefficient 3. So we will not have any representations like this. This will be converted to 5x squared plus 5x. That means each term, each exponent will have only one term. The last is the storage allocation of each term. So each of this is known as a term. So an x to the power n or ai x to the power I is known as a term in the polynomial equation. And if we have to store this in memory, it should be either in ascending order or it should be in a descending order. That is, the exponents either should be stored in this order: 2, 1, 0, or n minus 1. So the terms has to be stored in this order: 0, or it has to be started from 0 and then we can go till n. So either it has to be from n to 0 or from 0 to n. Now let us see how we can represent this polynomial with the help of array and with the help of linked list. Let us consider this particular example polynomial equation: 10x cubed plus 5. This is actually can be represented like this: 10x cubed plus 0x squared plus 0x to the power 1 plus 5x to the power 0. Now, in case of array representation, it is represented as a one-dimensional array where each of the index of the array represents the exponent of the polynomial. So in case of array, the polynomials are always stored in ascending order of exponent, because it is stored from 0 to n. So in this case, it is in the ascending order of the exponent. In array, the polynomials are always stored in ascending order of the exponent. And the second thing is that each index values represent the coefficient of the polynomial. So the index value means the positions which represents the coefficient along with the sign of the coefficient. So if we have to take this example polynomial, then 5 will be stored in this position because the x to the power 0, so the exponent is 0. That means it will be stored in the 0th position of the array. So this value will be 5. In the first, x to the power 1 has a coefficient of 0. So in the first index, it will be 0. Exponent 2 also has a coefficient 0. So it will be 0 in this place. And exponent 3 has a coefficient of 10. So 10 will be stored in this third index position of the array. So we can understand that in this case, if we are having, suppose, a polynomial like this, 10 x to the power 10 plus 2 x to the power 1. So we have to declare, in this case, we have to declare a one-dimensional array of size 11, but that array is actually going to use one-dimensional array of size 11 need to be declared, but actual utilization of memory space will be 2. So that's why if we are representing a polynomial using, like, for example, in case of sparse matrix, what we have seen, similarly, if we are using the linked list array representation of the polynomial, and if the polynomial is having very less number of exponents terms, then it could lead to a wastage of memory in case of the array representation. So that's why polynomial equations are also represented using linked list, which we are going to see next. In case of the linked list representation of the polynomial equation, the linked list consists of, each node of the linked list consists of 3 informations. One is the coefficient information, one is the exponent information, and the next one is the next term information, that is the address of the next term. So the implementation will be like this: struct polynomial int coefficient. We have considered coefficient like it is an integer type. You can take float also if it is a real number because you have told it. Int exponent and struct node star next. This next means the address of the next term. So if we look at this example of 10x cube plus 5, in this case, we can either store it in ascending order of the exponent, or we can also store it in the descending order of the exponent or ascending order of the exponent. So this is the descending order representation. So the first term is 10x cube. So 10 coefficient, 3 is the exponent. It contains a pointer to the next node, that is for the next term, which is 5x to the power 0. So 5, 0 and null. Even if this 0 may not be important in representation in this polynomial form, but it is important in case of the array or linked list representation, because the compiler have to understand what is that exponent, whether it is 0, 1, 2 or 3, and if we keep it empty, then compiler will not be able to decipher it. Also, we can store it in the ascending order. So we can either store 5, which is the exponent, the coefficient, exponent is 0, then it contains to the next higher exponent value. So 10, 3. Now, in this case, if we look at this particular example, 10x to the power 10 plus 2x to the power 1, in this case, even if there are only 2 terms, we have to reserve 11 memory spaces in case of array. out of which we use only 2 spaces. So the total number of memory spaces which is reserved in case of array is 44 bytes, out of which we use only 8 bytes. But if we look at the linked list representation of this case, so there will be total for each term, there will be 4 bytes for the coefficient, 4 bytes for the exponent, and because the address is integer type, unsigned integer type, so it will be again a 4 bytes. So it will be 4 plus 4 plus 4, that is 12 bytes for each term. Here we are having a total of 2 terms. So the memory space reserved in case of a linked list for 10 x to the power 10 plus 2 x to the power 1 will be only 24 bytes. So we see that in case of linked list, it does not matter what are the exponent terms present. It depends on the number of exponent terms present. So you see, in this case, we are having two terms. So in this case also the number of bytes reserved will be 24 bytes. In this case also there are two exponent terms. So in this case also it will be 24 bytes. Well, if we consider array, in this case the total number of bytes which will be reserved will be 4 cross 4 equals to 16 bytes. Well, if we consider this term, then it will be 44 bytes. Because in case of array, so we can conclude like this. In case of array, memory space reserved is equal to the highest exponent term plus 1 into the size of the data type into size of the coefficient. Well, if we consider that in case of a linked list, the memory space is in case of linked list, memory space reserved is equal to number of terms into 12. Usually, yeah, okay, we may not write it as 12, or rather the size of the structure. So we can write it like this. So if it is float also, anyway, it will be 12 bytes only because size of float is also 12. So it depends on the structure. So here it is the highest exponent term plus 1, and here it is the number of terms. With this, I conclude today's lecture. In the next class, we will be seeing the usage and the practical implementation of doubly linked list. Thank you.